everyone, welcome back to the course Deep Learning. Last time we tried to discuss about the introduction to deep learning, and today we'll continue to discuss about the concept of artificial neural networks. So, as we already mentioned in the previous one, we tried to see a different structure of deep learning, which is like a shallow neural networks and a deep neural network. So today let's see about the simple artificial neural networks, and we'll see how we can develop the models about the artificial neural networks. So let's start from the introduction part. What is a neural network? So it's neural network or artificial neural networks are simplified models, or we call it like shallow neural network, which is like related to the biological nervous system, or the idea or the concept of a neural network, which is comes from the human brains or human nervous system, and have been motivated by the kind of computing performance by the human brain. So, for instance, this diagram showed that the human brain. So, in human brain, there are different neurons here, and the signal will be just like transmitter from one neurons into the other ones by using like different connectors. So using like these concepts, researchers try to develop a neural network model. So this neural network, which is a type of information processing parameter, which is inspired by the biological nervous system, such as our brains. It's like, so that's why actually when you say that neural network, it will be used like different hidden neurons. That neuron will be just like take the concept from the human brain. So the structure of this neural network, which is large number of highly interconnected processing elements or neurons are working together. So here you see that, for instance, the first one is we call it input data, or data will be input into the input layers here. And this is the second one, which is like we call it hidden layers. So the first hidden layer is one, the second hidden layer is one. So we call it multiple hidden layers here. So this number of layers will be interconnected into interconnected, which is information will be just like processed throughout this one, which is like different level of hierarchies. And finally, there is the output layers, which is like display the output data, like a prediction and classification will be do in this one. The reason for this structure is like because of the number of layers, the model have the capacity to understand the data in detail about this one. So that is just the the concept of neural network. So like people, they learn from experience or by examples. So just like from the experience, will be try to understand from the data or from the experience like this. So human beings also just like learn from the experience, or maybe learn from the observation. At the same example, when it comes to neural network, we can give a data as an experience, and that model will try to understand or map the future from the data. And finally, that helps us to just like make some conclusion, make some prediction, make some classification, some generalization, or for any type of decisions will be important. So when you start from basic idea, complex nonlinear functions can be learned as a composition of simple processing units, or using like, for instance, with a list nonlinear function. So this NN, which is a collection of simple processing units or nodes that are connected by direct links or edges. So I think maybe everyone can understand about the neural network. So always when you start to neural network, will be just like draw like this one. This is an input layer, for instance, let's say, and maybe here there is different hidden layers here. Maybe so one or three is okay. So here is two different hidden layers. Maybe here also there are different hidden layers, and finally there are output layers. So what is AN is collection of a connection of simple processing units or nodes. Means actually this one is some nodes. So there are different nodes that connected with each other here, that show that the connection between here. So by connecting these nodes each other, we can try to just like increasing the understanding of the models by using different connections. So for instance, the first layer will be just like connected with the other ones. Let's draw like, for instance, like this. Sorry. So this one will be connected with this one. This one will be connected with this one. This one should be connected to this one. So each node will be connected with each other. So that means actually every node can access information from the previous one. That's just the technique of that what is just like looks like. So here also there is also like this a technique. Every node should be connected with each other. And this one is also like this. Finally, output layer and this one. So this one is we call it input layer. Input layer. Input layer means actually a layer that accepts a data or training data, and then the rest one, for instance, around here, we can call it. This one is we call it the hidden layers. Sorry. So just this is the hidden layer here. I'm sorry. This is just the hidden layers. That's just like hidden layers. And the last one is we call it the output layers. This one is the output layer. Output layer. So that is just a collection of simple processing units or nodes, means like connected with direct edge. Edge means like this one. So the connection that helps us to connect with each other. That's just the concept of neural network. So one edge will be connected with the second one by using a direct link. So this direct link means that you see that this one we call it the direct link that connect from this node, and this node will be just like that one. So from this one node, and the second node will be connected by using the edge. That is just we call it the neural network concept. So every node receives signals from the incoming edge. So that means, for instance, as shown here, you see that this node will be just receive signals from the previous one. So as shown here, for instance, this node will be just like receive information from this node, and this node also receives some information from this one, and like each other. Perform computation and transmit signals to the outgoing edge will be just like that, gives some information for the next one, and that helps to just learn more about the data natures. So like similar with the human brains, where nodes are neurons and signals are the electronic impulses. So in this case, actually just a node will be used as a neuron, like for in the human beings, and then the signals or the data will be just like the electronic impulses, like in human brains. So in neural network, when it comes to here, actually node will the neurons, and then the data will be just like the as a signal will be just try to help us to determine the outputs. In neural network, there is a weights of an edge that determine the strength of the connection between the nodes. So in each connection, we can try to determine or assign the weights for each connection. For instance, here, there is a weight here, weight for this connection, weight for this connection, weight for this connection, and any connection have a weight. So in order to just determine the strength of which connection will be the better one, that weight helps us to determine the strength of the connection for different direct links. So actually now let's start to see the simplest ANN, or we call it perceptron or single neurons. So single neurons means that there is just one hidden layer between the input and the hidden layers, the output layers. Sorry, that is we call it all simple layer. So this is just one layer, the second layer, and the third layer. So there is just one connection between this one and that. That's we call it just like the the connection between this one, the connection between this one, which is like so this is just only because of one hidden layer between the input and the output layer, that we call it simple ANN or perceptron. we call it perceptron, and let's see about this one. So perceptron means that the model is a symbol of interconnected nodes and weighted links. For instance, as shown in this diagram, it showed that from this one, the input nodes here, actually the node 1 and node here, showed that for this one. So this an input node, and the input node here, and this is the data that's input into the hidden nodes. And then this is just like the connection or the direct link that connect between different nodes. For instance, let's have one node here, and this is the first node, and then there is output nodes here. Y is the output node, and this is hidden layers, and this is an input layer. So between these input layers and hidden layers, or between hidden layer and output layer, we can just assign the weights. This weight is just try to determine the strength of the connection. So if weight 1 is like larger than weight 2, which means this link will just like have a better chance of determining the outputs. If this link will be just like better than the other one, which means this connection or this line will be just like have a strength to determine the output results. So the other one, so the summation of this one, it's showed that summation symbol, which means like data from this one, and this one will be just sum up, and then it goes into the output in order to determine the outputs. So that is, we call it just summation. And here actually also we can add like a bias, and then finally we have just the output nodes. That's just how neural network will be work. So the output nodes sum up each of the input values. So this one input, this one input, and this one input, and the output will be a combination of this one. For instance, let's see that an example. Let's see this number 9 digits, or this, let's say for instance number 9 here. In order to just like give number 9, for instance, we can just separate into different paths, and we can see that this one will be in different number. So first, let's draw that 0 first here. This one is 1, and maybe this one is 1, and this one is 1. So you see that now this one input, this one another input, this one another input. The combination of this one will be given number 9. So x1 maybe 0, and x2 maybe just like this arrow, and x3 will be just like these curves, will be just an example. So that showed that with different structures. That is just the output node will be the sum. So in order to say that number 9 will be just like using different shapes, and the combination of this one, finally it gives full information about whether this one is a digit 9 or the other one will be just the concept that showed that the difference concepts. Compare output nodes against threshold T will be just like one. So perception model will be shown that as shown here. Y is the output model, like this is the output as shown here. So this Y, which is like the output model, will be I is given actually this is, and the summation of weight is determined this weight, and Xi means x1, x2, x3, which is different input, and there is bias here. Or like this one actually just like the activation function that just try to determine the nonlinearity. So in deep learning, in neural network, actually we can try to use different activation functions in order to just like to determine the nonlinearity of the data. We'll see this one in detail in the next section. Maybe with that in the next slides. So just that's the concept of the perceptron. So this is a full structure that shows that how that the perceptron or forward propagation looks like that one. So always the input structure will be this one, and the weight is assigned for each link for this one, and then each input data will be just like summed by using this is a summation for this one, and here is nonlinearity, or we call it activation function. That just like, for instance, nonlinearity means sometimes the data will be just like nonlinear. So the data will be just, we can say that data may be like two types of data. The one is linear data, like this one. For instance, here is similar type of data here, and here is another data, for instance. So the two data will be separated by using linear lines. That is just like a simple type of data. But in complex data, there is no way of just separating the data by using a linear line. So that is, we call it linearity. So for that case, we need to use activation function. For instance, we have just like here, and we have a data, but in order to separate the data, maybe we need to move like this paths. The path will be just like different, so there is no any linearity. So for that case, the problem is complex, and identify the data will be very difficult. So for that case, we need to use or add nonlinearity. That means you need to check like with different paths. And this is just the output layer. So Y will be just like a type of output layers that show that the output. So this is just, we call it the output model. So the model made of a single neuron is called a perceptron, is like this one. And B is a bias. So actually neural network and in deep learning, weight and bias will be assigned by the model is automatically, but in order to just improve the performance, when we retrain, the weight and the bias will be changed. So this bias and weight just determine that actually how much like the model will be biased, and weight is to determine which link will have just like the highest weight in order to determine the classes or the outputs. That's just the combination of neural network. So this is like actually from the previous one, same with input, weights, some linearity, output. So the equation will be determined. So this one will be determined like this one. So what is the output? G is like nonlinearity, or we call it activation functions. And the summation, this one is show that the summation of M actually, just like, because here the weight is the number of link is M here, 1, then second, and M is just the number of weights here listed here. So I is equal to 1, it start from 1. Summation of xi and y. Xi is the input one, different input, and then weight is different weights. So linear combination of will be the equation is determined like this one in neural network combination. So that's why when we retrain again and again, actually the weight and the bias will be updated, and the performance maybe is like it's changed. So we need to tune some parameters in order to update the weights and the biases, and that helps to make like the neural network is just try to learn more about the data. This one actually also just like we can add also bias here in linear activation, and also bias is added here. Like for instance, the bias add 1 as a bias in order to determine the output. So just like this, also bias in weight just affects the output values on neural networks. So we cannot assign manually for this biases in weights, but this bias in weight is like assigned by the model. But in order to just like change this weight and biases, you need to retrain again, and at that time it will be change the value, and also the performance will be changed. This summation actually show that forward propagation, which is like almost similar with this one. So let's for instance, this is an example that shows that the single neurons here. So this is an image, which is a character, is 2. So this image will be just like first represented with different pixels here as shown here actually. So there are different pixels here, or like actually image will be represented with like ways like in terms of height and width. So here there are different like square for representation. So x1, x2, x3 means for instance only this part, only some part of this one. So from each square will be just like input as this one. So the combination of this input feature will be finally gives like whether this one is 2 or not 2, like that one. So x1, x2, xn is like, for instance, this is different feature as I already mentioned, like this one. For instance, if number 2 is this one, we can split this one is in different squares here. So we can put, or this one will be represented in different squares. Just the square. Sorry here. I'm sorry. So that means this square will be just as a 1 input, this one as 1 input. The second one, maybe this one is as a 1 input. The third one, maybe this one is as 1 input. And this one will be as 1 input, and this one will be 1 input. So that is x1, x2, x3 will be like this one. And weight is assigned, and bias is assigned. So the summation will be given finally. So by combining this one, if the output is 2, the y value is greater than or equal to 0.5, That means if the y value is greater than 0.5, using like that weight, which means that character will be 2. If y value is less than 0.5, like this one actually, the comparison threshold, that means we can say that this is the number is not 2. So this is just an example of a single neuron that only handles binary classification. So if like a single neuron, because actually the output value is just only one neuron, so that's used for only binary classification, that means the class is 2. So this cannot be applied or used for multi-class classification. So binary classification means, for instance, just the class will be 2. The class is only 2. So for that type, we can say that as binary classification, which is like it shows that the class will be either 2 or 1, either like 2 or not 2, 2 or not 2, 5 or not 5, like this type is, we call it binary classification. So this is also a layer of neurons that show that, for instance, this is why we call it binary classification. Is the reason is here. Show that. Okay, let me show in detail about this one. So, for instance, in this way, the output result is like only 2. It can say that the output is 2 or not 2. So that means we have 2 options. The output maybe it's 2 or not 2. That is just the category maybe from the 2 1. So that is we call it binary classification. But in the second one, here it showed that more than 2 options. So this is handwritten digit classification. It showed that the input is a character, and also there is different connection but in the output case, maybe the output is 1, maybe output is 2, maybe output is 3, maybe 4, 5, 6, 7, 8, 9, 10. So it depends on like the model. There is 10 neurons, which means 10 classes. So that is we call it 10 multi-class classification. So a layer of neuron can handle multiple possible outputs. So sometimes maybe when you write characters, the peoples or the like different people have different writing characters. So sometimes maybe when writes a number 2, it will be looks like maybe number 7. So that is why actually the class will be just like different types. In order to identify that one, we can try to define that, or we can try to use that, this type of structure. So here, the structure shows that the digit will be input into different structures, and then finally the class will be 10. And this is just the output, maybe 1, maybe 2, maybe 3, maybe 4, because of like the way of handwritings, and that there are different options. That type is, we call it, handwritten digital characteristics, especially for multi-class. So when we talk about neural networks, we call it perceptron forward passes. So perceptron forward pass means the signal will be just like the movement from left to right, so like which is called forward pass. So starting from, there is inputs, weights, sum, and nonlinearity here. So the left side, it shows that, for instance, the inputs are 2, 3, minus 1, and 5, and then the bias is 1, and the weight is given like 0.1, 0.5, 2.5, 0.2, and 3 for each edge links. There is summation, and then finally the output is y. So when you calculate, for instance, the equation for this one, g is given like each input times the weight. So g like 2 times 0.1 means the input value times the weight plus each connection. 3 times 0.5 minus 1.2, 5 times 0.1 plus 1 times 3.0. So this is just that determine the y value. So based on this one, if y value is greater than 0.5, for instance, we can say that digit will be 2 or not 2 or like the other output. So this is just the way how we can calculate the feed-forward propagation uses for this neural networks. So from the previous one, for instance, this it becomes the value is 3.2. So this one is the output is 3.2. That means yx is equal to g of 3.2. So g is represent the activation functions. So in the activation function, actually there are different equations for different activation function for the nonlinearity. So when you substitute that values here, 1 over 1 plus 2 is 3.2, which is 0.96. So based on this value, we can determine that the output values about the activation function also we'll see in this one. So this is the common training procedures in the artificial neural networks. Which means like we can say that the training procedure of the artificial neural networks or like model development procedure. So here let's see starting from training data. So always when we develop AN models or any machine learning model or deep learning models, we can start from collecting training data. So we need to have a training data. So the data should be split into training data and validation data or test data. So training data is for training the model, and validation data and test data will be kept in some way to test or evaluate the models. So the data should be normalized. So normalization is one step in the data pre-processing stage. So we call it data pre-processing. So that means like try to make it the data is ready to train the model. So data normalization, like for instance, we can just pre-process or avoiding unnecessary features, maybe just like filling missing values, or like for instance, making like checking into the data into by using like Minimax, we need to change the data into 0 and 1 formats like this one. That is we call it normalization. So we need to just make it ready the data. That is the second step. And then the third step should be training data. So in order to train the data that we use for training the data should be training data. So this one is training. And then validation. So validation is like the way of checking the training with using validation data. So in this validation, actually, we can use validation data from this one, or mostly actually for validation and training. From the training data, we can split the data like by using the different ratios. For instance, we can say that 80-20 with the percent. For instance, we can say, or we can split it by using 20-80 like this. So the split of 80 with like 20%, or 70%, and 30%. Most commonly, 80% for training and 20% for validation, and also 70% for training or 30% for validation will be the most common one. So you need to give like the data together. Once training and validation data is together, and you can split it into 80 and 20%. So the majority will be used for training the data. The rest of 20% of the data will be helped to test or validate the data. So validation means once the model is trained, in order to check that whether the model is trained well or not, you use some validation data to test the performance of the model. That's what we call it validation. So by using validation data, we can try to evaluate the performance of the model. So here actually, for instance, after validation, we can see that the performance of the model, if the performance is not good, we need to do hyperparameter tuning here. So we need to retrain again. Hyperparameter tuning means we need to adjust different parameters. So we need to change different parameters in order to improve the performance. So in hyperparameter tuning, there are different parameters that determine the performance of the model. For instance, in neural network, there are different hyperparameter tunings. So the first one, maybe let's say, maybe epoch. Or maybe the activation functions also on the other part. Activation function. On the hidden layer also the other one. Learning rates and optimizers. This like hidden layers or like a number of neurons will be just like different parameters that just determine the hyperparameter tuning that determine the performance of the model. So we need to tune that one. So let's say, for instance, at the beginning of the model or during the training of the model, let's say that we need to fix that the epoch may be just 100. Then, if the performance is not good, maybe later just like we can make it hyperparameter tuning and change it into the epochs into maybe this one is cancelled and we can try by making it into 200. That's just one hyperparameter tuning, just epoch. Also, maybe the activation function maybe is different. So next time we can try by using different activation function, and then we can retrain again, and we can see the performance. That's what we call it validation or change. Then, by using these repeated actions, finally we can get like the best models will be just available. So you see, training data, normalization is done, training is done, validation is done. So by changing different parameters, then we can say that the best model will be just is already got. So we got the best model or optimized model, which means the model achieves better performance. So we can say that this model is the best model. So we need to select that model. Finally, in order to say that if we have already a test model, a best model, or optimized model, or well-trained model, then we can evaluate this model by using test data or unseen data. Unseen data means the data that is not included in that training data. So which is like this data is a data which comes from the real environments. So maybe next time you have just some data that's collected from real environment, and then if you want to test that data, just bring that data and give for the best model selection or the selected models, and that model will try to predict or classify that data. That way it's like we call it the better ANN architectures will be this one. So basically, it's not the must to categorize into three. Maybe training data and validation data is okay. So test data maybe just like intentionally if you want to test by using some real data. So you can use also use just new test data from real world, and then you can evaluate the best model. And then you can see the performance evaluation. The performance evaluation will be evaluated using different techniques. Maybe the performance is evaluated by using accuracy, maybe by using like if this type of classification data, we can use precision, recall, F1 square, or like this type of metrics and confusion matrix. If it's type of regression models, we can use like mean square error, root mean square error, mean absolute error, or R square. Like there are different performance matrix techniques. So just use that one. By using that performance matrix, evaluate the performance. If the accuracy or if the precision is good, that means that model is good, that we can really implement or use for real world applications. That's just the procedure. For instance, this is an example of the perception example. So this is a sample data. So it's a type of supervised data. That means x1, x2, x3 is an input features, and y is like the output or a class, which is like the expected output. So when x is 1, x2 is 0, and x3 is 0, that means the expected output is -1. When x1 is 1, when x2 is 0, when x3 is 1, which means it's expected that the output is 1. So this is we call it targets, and this is we call it input features. So that is why in supervised learning, mostly supervised, when you say that supervised learning will be a combination of x and y. Data should be like this one. X is like including the training or input features. X is the input feature. Input feature. And what is this? Why we call it? What is a type of target, or we call it class? This is we call it target or class. We call it class. So in this case, x is x1, x2, x3 is input features, and y is we call it the target in a class, which means that when we give this one as an input, we means that we can expect this type of output. If the input is like this one, which means like the expected output or the class will be this one. just that. So this is the structure. Input is like this one. So x1 here, so will be like this one, x1, x2, x3 is given like input future, like from the table, and there is a black box neural network will be given, and the output will be like this one. So this is just y will be the output that determine the output of this one. Just this is the neural network. So you see that. So from the previous one, the same one, x1, x2, x3 is input into this one, and weight is assigned here 0.3, 0.3, 0.3, and there is a summation here. This is show that the summation of all three modules, and then as a bias is given 0.4, and finally this y is like the output module. So this is just the output module. That means y should be -1 or 1, -1 or 1, because our target is just only is a binary class. So from this one, -1, 1, 1, 1, -1, -1, 1, -1. That means our class is a 2 class. That means the class should be either -1 or 1, just -1 or 1. So the class should be either -1 or 1. So we call it binary classification, because we cannot just like the output would be expected from one of them. So the output cannot become -2 or -3 or 3, cannot be. So only the output from these two. Because of that one, we call it binary classification. That is just the type of deep learning. So when you develop the modules, actually the class will be determined. It depends on our data natures. So if our data nature will be just like a binary class, the output also binary class. So in this case, the data collected from the experiment, so from this one, it shows that only 2 classes. So that means the output result also either 1 or either -1. You see that? So if when you calculate this one, if x value greater than or equal to 0 like that, or if x value less than or equal to 0, so the class of the will be just like either 1 or -1. So 0.3 x1 means like 0.3 x1, 0.3 x3, 0.3 x4, I mean x3. And also there is a bias here, -0.4. So the finally, where you can get some value based on this one, it will help us to determine the class in perceptron examples. Okay, so now let's see real examples how we can implement artificial neural network. So let's say a data set like this one. For instance, when x is -1, y is -3. When x is 0, y is -1, like 1, 1. When x is 2, y is 3. When x is 3, y is 5. When x is 4, y is 7. So that means a data is there is class. So ys means y, xs means x, and then we have just machine learning or deep learning algorithms, and finally we can get a model. So let's see these examples. You see, so for the models, we have just a new data set. That data set is given for the models, and then we can get a generalization, a prediction, or the conclusion. So let's see, for instance, this is an example. So in neural network, actually, we can use just like different libraries for implementing this neural network. So model is equal to keras.sequential. For instance, this sequential actually show that when the data is like sequential, and there is a layers here. For instance, also here it will be determined like this one, and the shape of the data will be determined this one. And then this is a compile of the model, and the data will be shown like this one. So there is a fitting lines. So model.fit will be just model means actually that is the model is equal to means defined here. So the model will be created here. And then model.fit means x is x, y is a class, and the epoch, for instance, one of the parameters determined here. And then we can predict, like for instance, a new data here. So when x is 10, the model can try to help to predict the y values. Also just an example, which is we call it NN model development. So we try to see this one. So this is just a structure how like neural network concept can be related with the human brains. We already seen about this one. So NN model development is like a combination of 3 different structures: input layer, hidden layer, and output layers. So this is we call the layers. So sequentially, actually starting from the input layer, is like moving to hidden layer or connected with hidden layer, and then there is output layers will be just sequentially connected like this one. So let's see step by step how we can just develop NN models. So here there is model is equal to keras.sequential. So just this one, for instance, the first layer here. So one layer is created here. So here there is actually the number of the layers or the units will be also the number of the neurons is here, and the input shape is just one. And here actually there is also model.compile. So here we call it the model when you create here model is equal. So we can give actually any name here, model.compile. Just this is short that how we can just like start to compile a thread. And here we can adjust like optimizers and also the performance matrix. We call it loose. That is just performance matrix. I think also this is just hyperparameters SGD, which is like a type of optimizers, so like that determine the learning process. And this is the data. Then the model.fit, which is like the training will be started here. Model.fit, so already the model is defined here. But so by using the training data, X input features and the expected oral targets or corresponding target here, XS and YS, epoch is here. So epoch is equal to 500 means it will be iterated or repeated again 500 times for the training to understand the concept about these models. So if we like that, once the model is trained, next, like for instance, we can try to predict, we can give X value only. So here, because the combination of Xs and Ys, always for each X value have Y value, for each X value have Y value. So once the model is trained, we need to give only X value and the Y value will be predicted by the model. So when you give like, for instance, predict.10, then the model try to give the Y values by just like from the what he learned from the data sets. That's just how the NN model will be developed. So this is just, for instance, unit is equal to 1. That's just 1 neuron. 1 neuron means, for instance, here, the first layer is here, is input layer here. And the second one is, for instance, like this one. So here, just like if unit is equal to 1, which means like here, just only there is one nodes or one circles here. That's indicated about this one. And the input shape is equal to 1, just the shape of the image will be just 1. There is no like head and widers, that means a type of serial one. And then we start to compile the models or develop the models. So here actually we need to adjust the different optimizers and those functions. And this will be the data. Data is like, for instance, this part is the data part. So X and Y or training and test data is given. The main training part will be started here. So model.fit, always .fit is like, just like that indicates that the training of the model. So training will be done always by using training data. So XS and YS is the training data by combining that one, and we need to give and fix the iterations, and this will be given like this. So here actually, during the training, for instance, optimize our goals. If the optimizer of SGD, like here, make a guess, for instance, here it shows that you see here, there is a make a guess, like measure your accuracy and optimize your guess, like optimizer is a CGD, for instance, here given. So if the optimizer or the performance is not good, that means it will be just repeat the epochs, and then the epoch will be changed this parameter into 400, maybe 1000, and then retrain again. And that helps us to just again have a chance to retrain again and understand the map or the information from the data. That's we call it like the NN model development. Finally, is prediction or inference. So model.predict 10, which is like, for instance, when you give 10 as a test data, the model try to give the Y value here. That's just the neural network models. That's just a simple neural network models. Now let's try to see about multi-layer neural networks. So multi-layer neural network means that the number of the layers between the hidden and the output layer will be just like more than one layer. So we call it multi-layer neural network. So more than one hidden layer of the computing nodes between the input and the output layers. So every node in the hidden layers operates on the activate from the proceeding layers, and then this transmit the activation forward to the node of the next layer, like this one. Input layer, hidden layer, and output layer will be just like pass through this layer, but the hidden layer here is like 1, 2, 3, like a number of layers will be available from here on. So this is, you see that, for instance, when the number of the hidden layers will be increases, can be just like different features is extracted by using these labels. For instance, every hidden layer represents level of abstraction. Complex features are composite of similar features. For instance, here in the first layers, the image is not clear. You see that here is an image, so there is first level of abstraction. In the second step, it will be looks like the image is more clean than the first one. Here, you see like the eye here, the nose part will be just like try to make it clear. And third layer here, the image will be become more clean, which means like this layer means like this one. This is input layer, first hidden layer, second hidden layer, third hidden layer, and the output like this. So the connection will be like this one. You see? So in this case, maybe the image is like this one. In second case, maybe like this one. In third case, actually like, so this one may be in the output layer. So when the number of the layer is increasing, the images become more quality because the model understand about the image in detail. So the number of these layers is known as the pace of the NN. So this is just, we call it deep neural networks, or deep network will be, we call it multiple hidden layers. So when the model have multiple hidden layers, we call it deep neural network. So DNN, or deep neural network, means there is a number of hidden layers between the input and the output layers. This is an example that shows that the multi-layer neural network. So there is a number of hidden layers between the input and the output layers. Like simple neural networks, also weight and bias is assigned in each connection between the nodes. And finally, just like the maximum value will have just try to help to determine the output. So here, the inputs, like there's inputs here. Here, just like for instance, have an input. And layers, layer 1 here, layer 2 here, layer L is, and there is output here. So within each connection, weight and bias is assigned. Here is also weight and bias, and this connection also weight and bias. And finally, there is output layers. So fully connected, fully forward network, just like there is Rn and Rm actually from the input to this one. So the equation will be determined in order to find the outputs, like this is activation function, weight 1 x plus bias 1, just like this one, plus the second link will be weight 2 of alpha plus b2, just like for instance for this connection, because this one is alpha. The third one is like this one, and finally it gives like the output models. So this is just like YFX, which is like the combination of all these models will be, we call it like the output array. So just start an example. So for instance, so let's see some real examples about handwritten digit recognition, which is similar with the previous real code. So how just like NN or neural network or deep neural network will be help us to detect digits. For instance, this one. So you see, this is like, for instance, there are different handwritten characters. Like this one is, maybe it looks like maybe 5, maybe like 3. It looks also 3. So maybe someone can say that this one is 3, maybe someone is 5. So this is 0, 4, 1, 9, 2, like that one. But sometimes actually some handwritten will be like more difficult to identify that one. So we can give this image as an input for the model, deep neural network models, and the image just say that this digit will be 5. So like in natural language processing, in order to determine this one, it's a real example. When you see this one, for instance, this is like different human. This one is written by another person, this one another person. So like different way of handwriting. So in order to write one, like 2, for instance, you see there are different style of 2. 3, 4, also there are different handwritten characters by different peoples. So researcher actually, by using this data set as a training data set, the algorithm, deep learning or deep neural network algorithm, try to detect the characters or handwritten digit characteristics. So this is input layer. The image will be, or character is input here. There is hidden layer 1, hidden layer 2, and the output layer will be this one. So here 784 means because the image is 28 by 28, the height is 24, I mean 28, and the width is 28. So totally we have just 784. Hidden layer is like we can assign 1 to 8, and also we can assign activation function value. In second hidden layer, also the layer will be the neuron is 64, and the activation function is value. Just this is actually as a sample. Finally, the output layer, the class will be 10, and activation function is using the softmax like this, which means like this is 10 class, means the class will be just categorized into like 10 different digits from this one, because from this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the class will be 10 here. And the reason why this image will be, the height is 28 and the width is 28, that's why the input feature will be 784. So this is, it shows that the hidden layers, this is input layers, and this is output layers. So this one is just like, because of have more than one hidden layer, this one, we call it multi-layer or deep neural networks. So you see that 5 is given, 28 by 28 pixel input images. So totally we have just like 784 dimension for this image as an input. So finally the output for this one is maybe 0, maybe 0, maybe 1, maybe 2, maybe 3, maybe 4, maybe. So the output vector will be 10 dimensional, or one of one from 10 categories. So we don't know, because some digits in the training data, there are different number of images. So that image may be 1, maybe 2, maybe 3. So the class will be includes all the possibilities. That is why here the class will be maybe one of from the 10 one. So this one may be just like the class is 5, but other image maybe it becomes 1, other image maybe 3. So this is just a basic definition about like the simple neural networks and also multi-layer neural network. So the basic difference between simple neural network and the neural network will be just only the number of hidden layers between the input and the output layers. The other concept will be the other. So more the deep one, DNN or multi-layer network will be just have the capability to learn more complex things than the simple one, because when the level of layer is increasing, that is there is different level of abstraction, and that is help us to clearly understand about the data. Because of that, we call it deep neural networks. So in deep neural network, activation function will be the most important parameter in order to improve the performance of the model. So let's see about what is activation functions and what are like different activation functions. So this activation function, biological neurons or human neurons will be either active or not active, like that one. So we can see that this has a step function. For instance, non-activation and activated one will be determined like that one. In human brain also, there is active brain and not active brain sometimes. So just like this is a way of categorizing into two. So Bias tell us whether the activation will be happen or not, like the way of determining this one. So just we can model this behavior through like this one, by 0 and 1, for instance, active or non-active will be determined like this one simply. But let's see. So the purpose of activation function is to introduce non-linearities into the network. You see this data. In order, for instance, this data have two classes, read class and the green class. So in order to separate between the green class and read class, we need to use like this one, the path will be not straight line. It's non-linear line. So we need to move like this one and move to this one, move to this one, move to this one. That's just non-linearity. So if we didn't apply activation functions, the line should be only like this one. The separation will be like this one. If we didn't apply activation function, separation is only like this one. So you see, this separation is not perfect because in this data there is a still. So now the separation is not correct because this one is one class, this is another class, but in this class still have a green and red ones together, and then this one is red and brown. So activation function is just like to solve the problem of vanishing gradient problems or nonlinearity. So if we apply this one actually, let's say for instance, this. So nonlinearity means that in order to separate this data, we need to try to use nonlinear maps for separating this one. For instance, we can move like this one, we can move like this one, move like this one. And also maybe from here, like this one. So in order to separate actually the two classes, just use it. Nonlinearity will be the most important component. Nonlinearity is one of the most important. So what if we want to build this neural network is to distinguish green and red points. So the main objective is to distinguish between the green and red points, but in order to distinguish this one actually, it uses nonlinear points. So the purpose of this activation function, I just already mentioned that to introduce nonlinearity into the model that allow the network to learn complex features actually like this. You see, linear activation function means, as I already mentioned here, let's see that for instance, linear decision, no matter the network sizes, will be just using always like the linear lines or straight line lines. But in this one, nonlinearity, the purpose of this one will be different for the, let's see for instance. Okay, so from this one actually, just when you say that linear activation are shown here actually just separated by using linear lines here. So this one actually is not the accurate method to separate the two classes. So instead of that one, this is we call it nonlinearity. So nonlinearity allows us to approximate arbitrary complex functions. So this is the way how we can, for instance, separate the classes accurately for this one. So that's just activation function will be the most important thing to, especially to solve like more complex problems in that case. So this is just like without nonlinearity and with like for instance the other one. So without nonlinearity means actually just like deep neural network work the same as linear transform or just delta x. And nonlinearity actually with nonlinearity, network with more layers can approximate more complex functions like this one. You see like nonlinearity and more complex problems. So for instance, this is a no nonlinear transformation or just linear one. So the separation will be linear. So no input squashing problems in this one. So just the functions like this one. Input one here, x will be given and bias and weight is given, and the output will be given like this one. So the other one is actually in nonlinearity. You see that for instance the map between this one, which is like an example, it shows that the sigmoid activation function. So maybe I will give this one in detail about the different activation function. This one. So for instance, this is a sigmoid activation function. It's one type of activation function. So the equation of sigmoid activation function will be like this one. 1 over 1 plus exponential of minus x. So this minus x will be just determined from the output value of 1. Y is like here, g of zx, which is like determined, is equal to this value. So sigmoid activation function squashes the neurons output between 0 and 1. So always the data is between 0 and 1, as shown here. Actually, here is 0 and there is 1 here. So it's a type of bounded type of model. So if our data nature may be just like bound between 0 and 1 or so, that's maybe sigmoid activation function will be the best. So always it includes the positive value. So if your data nature have a negative values, maybe sigmoid activation function will be not be the best one. So this is just an example. The second is like tanh activation function, or we call it hyperbolic tangent. So in this case, actually, the squash the neurons output is between -1 and 1. So this type of activation function includes both the negative and the positive one. So both positive and negative, and it still is bounded because just between -1 and 1. So the data nature should be between these numbers, because when the data is changed or normalized, the data between bounded on this one and strictly increasing. So actually there are different, for instance, in the previous one, in sigmoid, just like it's good for binary classification. For instance, this one maybe it's better for binary classification, but still can cause vanishing gradient problems, or just it's very difficult to find that the optimal values or the distant values. And then when it comes to tanh activation function, actually just like a type of zero center, then the output may be -1 and 1 or bounded with this one. So this one also still just suffers from the vanishing gradient problems. So still actually this one, maybe it's not the best one, but actually the performance will be depends on the data nature. So you can try maybe tanh, sigmoid, and the other one, and then you can get that which one will be the best for your case. And the other one is ReLU, restified linear or ReLU activation function. So this one is the most common one. Recently, actually, this is most common used activation functions, and the fast and the simple one. And it's good for different type of data sets for this one. So in this one, actually, it will be bounded below by 0, always non-negative. So just like starting from this one, but actually the top one is not bounded, this one. So no upper bounded, just limit, there is no any limitation. So just positive, but the upper one is no limitation. Strictly increasing like this one, and tends to produce units with separate activities like this one here, and the advantage of for deep networks. So recently, most deep learning algorithm using this tanh, ReLU activation function for training the algorithm, because of there is no boundary or bounded on the top. So it will be just like including different data sets, and also have just less vanishing gradient problems, which is like finding the local minimum for that one. So because of this, our ReLU activation function is the best one. So it can be possible. Actually, there are also the other like softmax activation functions also. This is used in the output layer for multi-class classification. So softmax activation function mostly used in the output classes, for instance, or in the last layer of the neural network that is used for the multi-class classifications, and which is like the probability which is the same to be 1. So there are different activation functions that we try to use in the neural network model training parameters, and then you can try to use by changing different activation functions, and you can decide that which activation function will be important for your data sets. That's like, so just we can say that ReLU activation function is the fast and simple one and better one, but this will be sometimes is like different in different cases. It depends on the data nature. Then sometimes maybe tanh is maybe better than the ReLU activation function. So in order to say that just this one is the better one, you need to check like every activation function first. Okay. So the other concepts about like when you talk about neural network is about backpropagation actually. So what is like backpropagation means that this backpropagation is an example of supervised learning, which is that each layer to minimize the error between the layers response in the actual layer. So backpropagation means actually when you say that feed forward, start from the input layer and move into hidden layers and then output layers. And then when it backpropagation means then after the output layers, it will be go back to the initial one. That is just the way of checking the errors and the minimize the errors. That is just in order to reduce the error between the actual and the predicted data. So when in the back propagation, there is adjustment of the weights and the biases here. So in that case, that helps us to just improve the performance. So the error at each hidden layers is average of the evaluated error. So from this one forward and backward, so the error will become the average one. So this is just the way of back propagation. Actually, just neural network will be just using this property. So by default, it will be just the way of back propagation type of algorithm. So the error will be by using forward and backward checkings, and the average will be the average one. So this is just the way of how just like updating the individual network parameters propagated from the cost functions through the networks using the chain rule of the calculus. For instance, this one, you see like there are different one, weight x and y will be just like calculated using back propagations. So this is a procedure of the back propagation. Actually, just initialize the weights and biases. The first step, there is the initialization. And the weight in the network are initialized to random number from the interval of -1 and 1. So the weight will be given between these ranges or numbers. And each unit has a bias associated with this. So in addition with the weights, a bias will be assigned within like this one. And bias are similarly initialized between these ranges. And the step to feed the training samples. So the training sample will be fed into that one. And step 3 will be propagate the input for watts. We compute the net input and output of each units in the hidden and output layer. So actually, in each layer actually will be computed like here, will be like computed between the net inputs and the output within each hidden layers, and then will be calculated. So step 4 back propagation, the errors will be just like go back to the initial one by just like from outputs and the last hidden layer, and then the next one, and then finally until the first hidden layers. And it try to update the weight and bias to reflect the propagated errors. And finally, just terminating, the conditions will be like the way of back propagation. Okay. So just now we try to just see that the basic principles of neural network and how we can just build a neural network models. But when develop deep learning models, actually there are different problems. So next we try to see like what are that problems and how to solve that problems. So from that one, for instance, in deep learning, there is a problem of overfitting and underfitting problems. So let's see about the concept of what is overfitting and underfitting problems, and also we try to see that how we can just solve these type of problems. So in machine learning, generalization is the ability to perform well on the previously unobserved inputs. So making the training error is try to small, and making the gap between the training and the test error will be small. So in order to say that whether it's overfitting and underfitting, like we can just say that using the training and the validation errors, we can say that whether the model is underfit or overfits. So if the gap between the training error and the test error will be small, which means that if the training error and the test error is equal, which means that the model is understand well, so there is no any overfitting and underfitting problems. So first, let's say, before say that overfitting and underfitting problems, let's say that what is generalization. So generalization, which means like in order to say that once we train the model and then we test the model, and if the performance on the test result is, or if the accuracy is good, we can say that the generalization of the model is good. So perform well on the new and previously unseen inputs, which is like the generalization good. That means the classification performance, the prediction performance, or the other just tasks will be the better one. So that is, it means it makes a good generalization. So this is called generalization in the separate machine learning or deep learning for the optimization. For instance, this is some of the terminology that show that about the capacity, overfitting, and underfitting problems. So here, for instance, what is capacity here? So when you say that capacity, the complexity of function which can be represented by the module F. So here, the capacity will be low, capacity about right, and capacity too high, for instance. So this capacity means actually the model is trying to generalize the output is very well. So a capacity too low means which we can say that is underfitting, which is similar with underfitting. So this one actually, which is called underfitting. So what is underfitting means? So underfitting means a model is too simple, and does not achieve low errors on training data, which means underfitting means the training error is too high, and also model is too simple. Like traditional machine learning algorithms have underfitting problems, which is the capacity is become low. So here we call it, this one is the same with underfitting problems. And capacity at low means this one we call it like best model. So this is, we call it best. And capacity too high means actually this is just, we can say that overfitting. Overfitting problems. Overfitting. I'm sorry. Overfitting problems. So what is overfitting means? Like a training error is small, but a tested error is large. So let's say in underfitting problems, because of the model is too simple, the model is does not just like understand the data set. Because of that one, the model is not well trained. So because of that, the training error is become high. So this is an example. It shows that a red line will be just like the fitting line, and this one is the blue one will be the test one, and just the green one is just the type of noisy character. So this the blue dot data is not like near to the red lines or fitting lines. So this one means the models cannot be well trained, and it shows that is the performance is small. So here training load, error, and testing error will be high. In this case, we call it capacity about right, or we call it fitting models. So fitting model means like a test error and the training error almost become similar. So these dots or testing data will be fitting with the red lines, this one. And in the capacity too high, the model just try to understand the training data very high, but it is not good into the generalization or on test data. So for instance, we can train the model. The training error is small, but when you give unseen test data or when you give test data, the evaluation of test data will be the error is high. So at that time, we call it overfitting, which means the model try to capture and memorize the training data but then forget about when the test data is given. Because of just only like memorizing, it will be just forget about the details. So the testing data is become high errors. In that case, we call it overfitting problems. So in this case, because of that one, the training data show that like every sample will be just detected, but missing the generalization error. Testing error is high. That's why we call it the overfitting problems. So this is actually the basic RC deep learning. Especially deep learning most commonly actually have a problem of overfitting, not underfitting problem, because underfitting means like it's not well trained because of the capacity of the algorithm. So mostly traditional machine learning algorithms is simple algorithms, so there is no capacity to understand complexity. So because of that, mostly have underfitting problems. On the other hand, deep learning algorithm, because of the capacity of the model, they try to capture the data in the high ways. So just like that's just they try to memorize captured data, but sometimes they forget about the some of the information about the data. So because of that one, deep learning models have a problem of overfitting, but there is no problem of underfitting, mostly for overfitting problems. So let's see in detail about underfitting, what is underfitting, and then how like underfitting problem it will be happen. So in underfitting problem, the learner cannot find a solution that fits a training examples as well. So underfitting means the learner cannot capture some important aspect of the data. It will be just missing some important aspect of the data. It cannot capture. A reason for underfitting is happen. The one reason is the model is not rich enough, which means the model is not the best model, which means maybe you can use like less capacity models, traditional models. The other one is difficult to find the global optimum of the objective function, that is gradient, on the training set, and easy to get stuck on local minimum. It's very difficult to find the gradient distance for that one. And also limitation on the computational resources, especially on the training data. If the training data is small, or if the iteration is small, maybe underfitting problem is the same. For instance, epoch is the one parameter that we need to adjust on the neural network. So if we adjust the epoch, for instance, just 5, that means just only it iterates 5 times. So at that time, maybe before the model can understand the data, it will be stop iterations or stop training. At that case, it will be happen underfitting problem. So we need to give just like the beta epoch or iteration size, also data size will be have an effect. So in these underfitting problems, model does not have the capacity to fully learn the data. So this is most commonly happen in non-deep learning approaches, which means like in traditional machine learning algorithms, where large-scale training data, maybe the data set is large scale, but the algorithm will be very simple. This is maybe just like try to cases underfitting problem. So let's say you have like image-based data, but you use like just like simple machine learning algorithm, let's say SVM. So for that case, the underfitting problem will be happen because of SVM cannot be captured or understand very well for that image-based data. So we need to select a data that fits with our data natures, or I mean a model that just related with our data models. So for a large amount of data, we need to we need to select deep learning algorithms rather than the simple or traditional machine learning algorithms. The other one is overfitting. So when you say that overfitting is too complex, extra parameters does not generate it well. So just only like the learner fits the training data well, but uses their ability to generate well. That means it has a small training error, but larger generalization error or larger testing errors. So a learner with a larger capacity tends to overfit when the family of the function is too large compared with the size of the training data, and it contains many functions which all fit with the training data well. Or sometimes maybe if the data size is too small, overfitting will be happen. So we need to just give like, or we need to have a big amount of data. Either if the data is small, maybe the algorithm will try to just like understand that data very well, but just like when you give test data, maybe it does not recognize very well for each features of the data. So that's just overfitting problem will be happen. But the other one is just like maybe sometimes actually maybe noise is also just creates overfitting problem. So data contaminated by noise will be also it leads overfitting problem. So before training the data, we need to clean the data, we need to be arrange the data, we need to be pre-process the data. So that will be just help us to improve the performance of the model. So the learner with a large capacity tends to describe random errors, and this node will be just like making underlying the models of the data. Because of that, overfitting will be happen. So this is, you see that, for instance, this is Ideal fitting means the best one, which is well-trained model or optimal model. So ideal fit, for instance, the middle one is ideal fit one. So the data will be fitting with the curve, well, the blue line that is near to this one. So it shows that which is the best model. The left one is under fitting. So actually you see as linear one. So the data just a straight line, but this one is red one is plotting into different futures. So which is the model does not have a capacity to fully learn the data. And this is overfitting. The data is too much concerned on the training, but forget about the test. So it try to plot like each futures, each data. So it's like if there is too much up and down on this plotting, that is just the graph will be overfitting problems. So the line always just like this type of curves, if like the ideal fit one. So when you describe like based on a capacity and errors, for instance, around here we can say that optimal capacity, because the training error and the validation error will be just like have a small gap here. Training error is blue one, and the green one is a generalization error. So the gap between these two is close. So that case is, we call it optimal capacity. But in this case, underfitting problem, just like at the beginning of the iteration, the model is not trained well. So because of that, here, the model just try to have a big training error and the test error. So we call it underfitting. And around here, there is a big gap between a training error and generalization error. So if the gap between generalization error and training error is high, which means like the model have a small training error but have a big testing error, that is just, we call it overfitting problem. So always when you train a neural network model, deep learning models, you need to just check that the training error and the validation error. So if that two, or the curve between training error and validation error is not convergent, which means like it has overfitting problem. So you need to solve these type of problems using like different techniques. So here, like for instance, you said, let's say this is a graph that shows the different iterations and the errors. So the training error and generalization error is shown like here. So there is a big gap between these two colors. So this is just, you say that the overfitting problems. So with different actually polynomial degrees, for instance, this is for like when the degree is 0, when degree is 1, 2, 3, 4, 5, like the generalization error is different. So when the degree of polynomial is 0, almost the training error is and generalization error is similar. Degree 1, degree 2, degree 3. But when the degree is increasing, actually, there is overfitting problem will be happen. This is just in the type of polynomial type of equation, like for instance, like have more than like cubic or like square. So in that case, actually, also by changing the degree of the polynomials, we can try to just see that the overfitting problems or the errors. So here, actually, just like when just using different polynomial, the overfitting will be just different. So around here, we can say that good one, because the two will be just like near each other, but here the gap will be high. So in that case, we call it overfitting problems. So we need to select the model with the smallest generalization error. So always when you select the best or optimal models, you need to select the model that have best or smallest generalization error, which means small training error at the same time small test error. So if the model have small testing error and small training error, which means an optimal model or the best model that have the capacity to predict or classify the data accurately or a better generalization performance. So in general, this is, we call it a generalization in capacity. This graph shows that the generalization in capacity. So this generalization shows that the generalization cap is high. This one is optimal generalization, and this one is underperforming zone. So like because here actually there is no any learning here, it's 0. So because of that, actually it's like at the beginning there is underfitting problem, in the middle, which is best capacity, but when the iteration is increasing, actually the gap is high, that is called generalization gap. So as the capacity increases, training error can be reduced, but the optimum, the difference between training and generalization error is increased. So this way, so we call it overfitting problem. So at some point, the increase in optimism is larger than the decrease in training errors. So we enter the overfitting region where the capacity is too large above the optimal capacity, like this one. So overfitting zone will be started like here. So before reaching optimal capacity, we are in the underfitting region, actually at the beginning. So this is just that shows that the relationship. So maybe around here we need to select the iteration around here in order to ask the best model for this case. Actually, when you talk about like overfitting and underfitting problems, just like we can see that bias invariance also like the cause of overfitting and underfitting problems. So, for instance, when you say that bias, a model has either low bias or high bias. So, low bias means a low bias model will make fewer assumptions about the form of the target function. So, low bias means like predicted value is near to the actual value, which is almost accurate. So, low bias is better than the high bias. So, if the model has low bias, which means that the predicted error in the actual error is, or the predicted value in the actual value is almost similar. So that is just like the good ways. High bias is, in high bias actually, the model with high bias makes more assumption and the model becomes unable to capture the important feature of our data set. So this high bias model cannot perform well on new data sets, which means that the predicted value is more far away or more different from the actual value, which is we call not accurate. That's led to underfitting problems. So the actual value and the predicted value is different. So because of this high bias, just underfitting problem will be happen. So here you see that in high bias, this area is, we call it underfitting areas, which means in this case, the model cannot be capture important features from the dataset, or the model cannot learn important features from the dataset. Because of that one, the training error and also the test error will be high. So bias will be just like it leads to underfitting problem, especially high bias. And then the other one is variance. Also, the model that shows high variance learns a lot and performs well in the training dataset, but does not recognize well in the unseen dataset. So variance means actually also the model have the capacity to learn more about on the training dataset, but just like it's not generalized on the test dataset or the unseen test dataset. So the model, it looks like good result with the training dataset, but shows high error rates on the test dataset. So low variance means there is a small variation in the prediction of the target function, which means like group of predicted value does not be scattered with each other. So here you see like high variance means actually there is also overfitting problems here. So in high variance result, which means that the training error and the validation error will be just like very far away. So in high variance, a group of predicted values does scatter with each other, which is overfitting problem will be happen. So high variance is the same as overfitting, and also high bias, which is the same as what? Underfitting. So if we say that high variance, which means there is overfitting problems, and also if say that high bias, which means there is what? Underfitting problems. So the middle one, this one is, we call it like the optimal, the best one is this one. So this is underfitting, this one is overfitting, but the middle one is the optimal one, which is, we call it the best model. So we need to try to arrange the bias and variance. So in machine learning, deep learning, we need to just adjust the bias and the variance will be adjusted. So actually bias value arranged. So to solve these problems by tuning different parameters, yes, it can be possible to solve this one. So this is, for instance, graphic illustration of the bias and the variance with this one. So low bias and low variance, which is a good model. So here you see that all data will be captured here. So the best model is here. And low bias and high variance, actually there is here. So there is a problem of overfitting here. High bias and low variance is a problem of actually underfitting problems. And high bias and high variance is totally overfitting. It's almost the data is out of the bound, or which is called outliers. So because of that one, we need to try to just adjust the variance, and the bias will be adjusted in order to reduce the overfitting and underfitting problem. So this is actually the most common problems that we need to be addressed by using like different techniques. So this is the bias and variance trade-off. For instance, here underfitting and here overfitting. So at the beginning there is underfitting problems, and finally the test error is high, but the training error is small. You see here, test error, training error is become reduce. This is high, but become low. But testing error is become, this one is high and become down, and again increasing. So here the gap between test error and training error is start to increasing. So this case we call it overfitting problem. You see that? So when have many training examples, because of this one, the training error is like reduced, but few training examples there is overfitting problem, and they are like here. So bias and variance trade-off, which is like this is underfitting zone. Overfitting zone is this one, because actually the gap starts between this one, and the optimal is this one, because here, as shown in the diagram, almost this the brown one and the blue line is almost close here. And this one actually is close, but still is underfitting problem, because the model still cannot be captured important features from here, or because there is high bias, so there is underfitting problem here. In this case, the model can capture most important parameter from the training data, but forget from the test data. So because of that one, there is overfitting problems. But the middle one will be just like the model, the best one. So we need to select around here, because, so for instance, here iteration is 5, here is iteration is 50, here is, let's say iteration is 100. So which means at iteration 50 will be, we can get the best model from this training. So we need to use iteration until 50 maybe enough, rather than iteration until 100. So that is why we need to change the epoch number in order to get like, or in order to see that whether there is overfit or underfit problem. So first you can try by using 50 epoch, and then 100, 500, and that will be showed that in which iteration will be achieved the best performance. So this is actually the equation that showed that the bias and variance, which is I think not importance. And there are different techniques for the solving this variance, overfitting and underfitting problem. For instance, the first one is cross validation. I think we can try to see about this one. So this is about the avoiding overfitting problems. I think maybe it's better to see this one on the next classes. So I think we can say that already there is a problem of overfitting and underfitting. So to solve this overfitting and underfitting problems, we need to use different techniques for solving this problem. So we'll try to see this one in the next class. So I think this is enough for today's class. So today we try to see, just to summarize that, an introduction about deep learning and about neural networks and overfitting and underfitting problems. So in the next class, we try to see about how we can avoid overfitting problems, because most specifically in deep learning algorithm, overfitting will be happen. So the problem mostly is more concerned on overfitting. So we'll more focus on that one. And next to that one also, we try to see about in the next class about the CNN, about the RNN we'll try to see this one in the next classes. So thank you very much for today's class, and see you for next class. Thank you.